Okay, so today we'll be doing chapter 4. 4.1 is just the introductions to magnetic field, and all those questions will come out as objective questions in your UPS. Okay, so for 4.2 and onwards, these are the knowledge needed in order to answer your assignment, and also you need some of it in order to answer questions in chapter 5. So before we start, actually there's a trick on how to answer these all these questions in chapter 4. The most important thing is to identify the object, the things that you're looking at. So for instance, 4.2 is talking about magnetic field, okay, resultant magnetic field. So magnetic field, you have magnetic field coming out from a different object, okay. So first of all, if you recall the things that we learned in tutorials, in the lecture, first, if you have a stationary charge, then the charge itself, it gives you electric field. If the charge is moving, then the charge will have electric field and also magnetic field at the same time. If this charge is moving inside another magnetic field, then it will give you magnetic force. And in this subtopic, you are looking at magnetic field produced by current carrying conductor. How many types current carrying conductor can we have? Okay, so we are talking about current carrying conductor. Okay, current carrying conductor. So the first type is what we have a straight conductor, which is a straight wire. Okay, a straight wire. When it comes to a straight conductor, then the equations to be used is B equals to mu naught I over 2 pi r. This is the equations for straight conductor. So first things, when it comes to calculating electric field and electric force in chapter 4, you try to identify the object first. Okay, so the first one, straight conductor. The shape is a straight line. Okay, so it could be a wire, it could be a, questions could mention it as a wire, could say a straight conductor, or any other thing that is in a straight line form. And then the second types of the conductor that we have is the coil. Okay, it's a coil. So coil in this case, we refers to a circular coil. If you have a rectangular coil, then basically it is formed by 4 straight conductors. All right. So circular coil, the second example is. So when it comes to circular coil, equation is B equals to mu naught Ni over 2r. Okay, mu naught Ni over 2r. Now this n, okay, this n, it depends on how many coil you have, how many coil you stack them together. For example, if you say n equals 3, then you have 3 coil, and then you stack them together. So they will give you a coil looks, okay, coil looking thing like this. So you have 3 coils stacking together. Okay, you stack them together, so it becomes a 3 coil with an n equals to 3. Okay, the B equals to mu naught times 3I over 2r. So that is the meanings of 3 coil, multiple coil. Then the last one, okay, the last type is a solenoid. So if you have solenoid, then the equations is B equals to mu naught small letter n I. Now this small letter n is important. All right. Sometimes questions will tell you, okay, now you have numbers of turns per unit length. Okay, this is a number of turns per unit length. Basically, it means a per meter. In 1 meter, how many turns you have? Okay, so sometimes questions won't give you small letter n. Questions will give you capital letter N with the length of the solenoid. Okay, capital letter N with the length of the solenoid. So in that case, you need to know how to calculate the small letter n, right? So now when it comes to multiple turns solenoid, what does it mean? It means that you have a spring-looking things, a helix shape, okay, with 1 turn, 2 turns, 3 turns. All right, so now you have 3 turns, n equals to 3. So when it comes to coil, 3n, n equals to 3 means you have 3 coil, but you stack them together. When it comes to solenoid, if you have 3n, n equals to 3, then it just means that you have 3 turns along this solenoid. Now, solenoid, there are two possible cases. The example right here, the equations right here is for central. Okay, another one is at the end of the solenoid. Okay, at the ends of the solenoid, where the B is just going to be equal to half of the magnetic field strength at the center. So you just divide by 2. Okay, so this is at the end of solenoid. This is at the center of the solenoid. So once you're able to identify the types of the object that you're looking at, it shouldn't be an issue for you to solve the questions. Why? Because you have just one equation for each object. When it comes to straight conductor magnetic field, you have just this equation. When it comes to circular coil, the magnetic field, you just have this equation. When it comes to solenoid, if you ask you to calculate center, you have this one equation. If you started to calculate the magnetic field at the end of solenoid, then you have just one equation. Okay, so there's nothing much to do. All you have to do is to select the right equations according to the objects given. That's why for me, personally, I like chapter 4 very much. Okay, it is a waste for it to not coming out in your PSPM because it is such an easy questions, easy to score chapter. As long as you know whether you're looking at the magnetic field or magnetic force and what type of object you're looking at, then you just pick the equations, pop, done, you get the answer. Okay, so now it's coming out as your assignment, so you also need to know which equations to use. Alright, dia rugi. Okay, rugi tak keluar di PSPM, tapi apa yang boleh dibuat? Tak boleh buat apa-apa. Kita belajar saja, bersedia untuk assignment kita. Okay, now let's look at example 1. Okay, example 1, a long wire carrying, okay, now you are given a long wire. A long wire, usually it represents a straight conductor. Okay, a straight current carrying conductor. So carrying a current 30 ampere is placed parallel to and 3 cm away from a similar wire. So it has two pieces of information is given in the first sentence. You have a I that belongs to X and also the distance. Okay, the distance between the first and the second wire. And the second wire is carrying a current of 6 ampere. Okay, IY. Find the magnitude and directions of the magnetic flux density midway. The keyword is midway. So you have two wire X and wire Y, and you want to find the magnetic fields midway between the wire. So let's look at the diagram in 3D form first. Okay, now you have a diagram. This is a 3D diagram. You have a wire, conductor X, and then you have conductor Y. Okay, conductor Y. So the distance between them is 3 cm, right? The distance between them is 3 cm. According to the question is asking for magnetic flux density, which is your B, midway between the wire. Okay, so this is midway. So from here to here, it's 1.5. From here to here, it's also 1.5 cm. So these are the information that we have right now. So according to questions A now it tells you current are in the same direction. So it is up to you to decide whether you want both current heading up or both current heading downwards. Okay, it's totally up to you. So for example, now I want both of them, they're going up. So this is my IX, this is my IY. Now, when it comes to this type of questions, actually, I don't encourage you to use 3D diagram, even though it looks so much nicer. Why? Because it will be a bit hard for you to describe the direction, for you to imagine, for you to see the direction. Okay? Now, of course, for me, I'm used to this type of questions already. I know when my X, okay, when my current IX is heading upward, the current is into the page at the midpoint. Okay, let's say this is point A. If my IY is heading up, the current, the magnetic field generated by IY is heading out of the page. For me, it's easy. Why? Because I'm used to this type of questions. I'm used to it already. Now, for you, a new learner, you're new to this topic, I would encourage you to sketch the diagram from top view. Okay, but of course, if you think you're confident enough to use a 3D diagram, it is totally up to you. Okay, but in exam, I would encourage you to use a top view. Okay, so let's say top view. Okay, this is top view. Now I'm assuming both current heading up. So this is my IY. If heading up, it is out of the page. So this is my IY. IX. Okay, this is my IX. This is my conductor X. This is my conductor Y. So this is a IY. Okay, this is IY. So IX and IY. So both of them, they are out of the page because I'm assuming my eyes is located at the from top. Okay, I'm viewing it from top. So if I view it from top, how am I going to determine the directions of the magnetic field when it is at point A? So this is point A. So it's very simple. You just use your right hand, you grip your right hand and let the thumb pointing towards you. Because according to the diagram given right here, IX is out of the page. So if it's out of the page, okay, the magnetic field generated will be like this. Okay, the magnetic field generated will be like this. So it is a circle. Okay, it passes through a point A. So you turns your right hand grip, okay, your right hand, you turns it until the four fingers reaches a point A. Then you see what is the directions of your fingers. Okay, so at this point, your finger will be pointing upwards. So this is your BX. The B coming from conductor X. Okay, so you hold your right hand, you let the thumbs pointing towards you, you put it on top of IX, and then you rotate your hand slowly. And look at your fingers. Look at what is the directions of B when your forefinger it touches point B, when it's located on top of point B. All right. And then you just repeat the same thing for IY. Okay, IY, once again, now the directions of the magnetic field, the shape of the magnetic field is a circle. So you hold your right hand, you let your thumbs pointing towards you, you place it on top of IY, and then you rotate your right hand slowly. And look at the directions of your fingertips when it reaches point A. Okay, when your right hand rotates, it reaches point A, your finger will be pointing downwards. This is your BY. Okay, so one up, one down, meaning that now you have one positive value and one negative value. Then how are we going to find the magnitude and the direction? So let us begin with magnitude. If you recall the things that we learned in chapter 1, how to calculate resultant electric field, before we do a resultant and resolving vector, we must first calculate the values of B. Okay, we need to calculate the field, the strength of the field first. So you calculate Bx and calculate By separately. So Bx is equals to mu naught I, now Bx Ix, because Bx is being generated by Ix. Ix is a current flow. Inside current, we got charge. Charge flowing give you magnetic field. Okay, so Bx is being generated because of Ix. So over 2 pi Rx. So Rx is basically half of the distance, okay, Rxa. So the distance between X and A, which is 1.5 cm. So you expand the equation. Now, mu naught is a constant value, which can be found in a list of constant. So 4 pi times 10 to the power of negative 7. Ix given is 30 ampere. And then 2 pi, now remember to change the R into SI unit. We have 1.5 cm, so it is 1.5 times 10 to the power of negative 2. So eventually, you will obtain Vx equals to 4 times 10 to the power of negative 4 Tesla. Okay, and then it is upward. Okay, it is upward. So you repeat the same thing for Vy. Okay, mu naught Iy over 2 pi Rya. Plug in the value, and you should obtain 8 times 10 to the power of negative 5 Tesla. And this is downward. Okay, this is downward. Right, one up, one down. So now how are you going to do it? Okay, you want to calculate the total magnetic field at point A. So BA is then equals to, now, since BX is going up, BY is going down. So BX plus a negative vector Vy. So negative Vy, because this is going downwards. Okay, it is downwards. Therefore, it is equals to 4 times 10 to the power of negative 4 minus 8 times 10 to the power of negative 5. So resultant magnetic field is equals to 3.2 times 10 to the power of negative 4 Tesla. Okay, 3.2 times 10 to the power of negative 4 Tesla. So since you use Bx minus By, upward minus downward, and you obtain a positive value, it shows that Ba is going upward, right? Ba is going upward. Now, if you stick to the 3D diagram, okay, if you stick to 3D diagram, then what is going to happen? You will get Bx that is pointing into the page, okay, into the page. And then your By would be out of the page. And your final answer eventually will be into the page, right? Into the page, because your Bx is larger than By. So it is up to you whether you want to use this 3D diagram or you want to use this 2D diagram. As long as you show it in your answer, let the examiner know how it looks like. Okay, how the diagram looks like. Whether you're reviewing it from the front view in a 3D diagram or you're looking at it from the top in a 2D diagram. You can also view it from bottom. Nothing's wrong. Okay, nothing's wrong. It all depends on your diagram because diagram is not given by the question. Okay, soalan tak bagi kamu diagram, soalan tak beritahu kamu current going up ke, going down, dia cuma beritahu kamu current in the same direction. So ada banyak possibility. Okay, dan dari arah yang kamu tengok, okay, if you are viewing it from a different angle, different perspective, then you will get different final answer. Okay, some of you, if you are viewing it from bottom, if you use bottom view, then you're going to get VA is a negative value. Why negative? Because you're viewing it from the bottom. That's it. Nothing's wrong. Okay, nothing is wrong. So just make sure to show the diagram so that the examiner know you're looking at the object from where. How does it look like? Okay, what is the directions of the current flow? Okay, so now let's look at questions B. So questions B, now what you have right here is that it tells you now you have two current, they are in opposite direction. So rather than two current going up, now your conductor X, let's say, is still going up. Okay, your Ix is still going up. And then your conductor Y right here. Okay, your conductor Y, now I let the current flowing down. Right, and the distance between them is still 3 cm because the question didn't say about anything about the distance between the wire. So we assume they are still being kept at the same position. The only thing that has changed is the direction of the current flow. So now let's assume you're viewing from the top again, okay, top view, right, top view. So this is X, this is Y. So if you're viewing from the top, Ix once again is out of the page, but now what happens to Iy? It is into the page. So you have a cross right here. Okay, you have a cross right here. So again, point A is the midpoint. You just repeat the same thing. So your Bx, if you use a right-hand grip rule, Bx is going up. If you use a right-hand grip rule for your conductor Y right now, okay, you hold your right hand. Now the thumb, you let it pointing towards the screen, okay, towards this cross on top of your screen, and then you slowly rotate your hand. And you will see that when your forefinger reaches point A, they are all pointing upward, okay, they are all pointing up, they are all heading upwards. So that is a diagram for if the current is in the opposite direction. So now both Bx and By, they are heading toward the same direction. Well, you're still using same current, the distance, they're all still the same, meaning that you can use the B from questions A. Okay, your Bx is still 4 times 10 to the power of negative 4. Your By is still 8 times 10 to the power of negative 5. Right? So my Bx is still 4 times 10 to the power of negative 4 Tesla. By is still equals to 8 times 10 to the power of negative 5 Tesla. So my BA right now, my new BA, my BA in a questions B would be equals to BX plus BY, okay, which is then equals to 4.8 times 10 to the power of negative 4 Tesla. And now this heading upward. So that is how you solve it. Okay, that is how you solve it. It's not hard, just that you need to you need to sketch the diagram first. Okay, once again, diagram plays a very important role in problem solving. And also in your assignment, you must show the diagram. Okay, you must show the diagram and then show the examiner which equations that you're using. Okay, before you solve it, before you do the substitution, you must follow the step. Start from diagram and then followed by the equations. After that, okay, then you can start to do the substitution. And at the end, you show your final answer together with the direction. Okay, together with the direction. So that is how you solve questions in chapter 4. All right, so now I give you 5 minutes to write down the summary. Okay, we have a summary right here. So 5 minutes for to write down the summary, the answer for questions A, and also the answer for questions B. If you have any questions, you may ask. All right. So that is first questions, example one. Okay, example one. And that is the hardest questions that can be found in finding resultant magnetic fields type questions. Okay, kalau Anda faham soalan ini, basically untuk kira resultant magnetic field, memang tak ada masalah dah. So ini soalan yang paling rumit yang Anda boleh dapat. Alright, so let's look at example 2. Example 2 is just a very short and very simple questions. As you can see here, a closely wound circular coil. Now, your object is a circular coil right now. You see, even before you start to look at all of the information, you already know which equations to be used. Okay, kamu sudah tahu equations mana untuk digunakan sebelum Anda tengok maklumat yang diberi. Why? Because this is a magnetic field questions and you're given circular coil. There's only one questions, okay, one equation that can be used, which is B equals to mu naught Ni over 2R. This is the only equation when it comes to circular coil. So a closely wound circular coil of a diameter 10 cm. Okay, 10 cm. This is the diameter. Okay, so you need a radius. So D equals to 2R, which is equals to, okay, R is equals to D divided by 2, which is then equals to 5 times 10 to the power of negative 2 meter. And then it has a 500 turns and the car carries a current of 2.5 ampere. This is the I. This is the magnitude of the magnetic field. So the question just asking for magnitude, you don't have to mention the direction. Okay, and of course you cannot mention the directions if there's no diagram. All right, in this type of questions, if question asks you to determine the direction but you're not given the diagram, then you need to draw your own diagram. Okay, Anda kena sendiri lukis diagram. Kalau Anda diberi soalan macam begini, tetapi dia minta Anda tentukan magnitude dan direction, maka Anda kena sendiri lukis diagram. Otherwise, you won't be able to show the direction. And the examiner also don't know whether you got the right directions or not without diagram. So you need to show the diagram. All right. So since this question is just asking for magnitude, therefore no diagram is needed. So you just plug in the value. So epsilon naught is 4 pi times 10 to the power of negative 7. Number of turn is 500. And then current is 2.5 divided by 2R we have it here, which is a 5 times 10 to the power of negative 2. Okay, so the final answer is 1.57 times 10 to the power of negative 2 Tesla. Okay, 1.57 times 10 to the power of negative 2 Tesla. So I give you 1 minute to write it down because this is just a very short and simple questions. So before we proceed to the next example. All right, now let's look at example 3. Okay, so wait, yeah. Oops. Okay, example 3. Example 3, now you have a 2000 turn solenoid. So now you see you have the object known as solenoid. So once again, before you answer the questions, you already know what is the equations that you can use. Okay, depending on the questions on where is the object. So a 2000 turns, okay, that is your N of length, that is capital letter, small letter L, sorry, and the resistance R is connected to a 20 volt. Aha! This question is a bit special. You're given resistance and also power supply. Find the magnetic flux density at midpoint, you see? Midpoint of solenoid, center of solenoid. For instance, you know the equations to be used is B equals to mu naught Ni. Now, of course, these equations cannot be used straight away. Why? Because you don't have small letter n. But what you do have is the capital letter N and L. Therefore, we're going to expand these equations into mu naught Ni over L. But I have a questions again. I don't have I. So what happens right here is now you have 2000 turn solenoid that is being connected to a power supply, right? So this solenoid, it has R equals to 16 ohm and then V equals to 20 volt. So they are being connected in parallel, meaning that when this one, okay, when current flowing through your solenoid, V across solenoid is also equals to 20 volt. So from here, you can then calculate the current flowing through it. So I is equals to V over R, which is equals to 20 over 16, which is then equals to okay, I wait, yeah, 1.25. Okay, 1.25 ampere. So now that I have everything, so I have N, I have I have a L, and then the mu naught is just a constant value. You plug in everything, and eventually you should obtain 7.85 times 10 to the power of -2 Tesla. Okay, -2 Tesla. So 7.85 times 10 to the power -2 Tesla. So that is questions A. So questions A, a new thing is how to calculate I first before you determine the magnetic field. Now questions B. A solenoid of length 1.5 meter and 2.6 cm in diameter. You have a length and then you also have a diameter. Why? So it carries a current of 18 ampere. The magnetic field inside the solenoid given is 2.3 millitesla. This M is stand for milli. Okay, so 2.3 millitesla. So it's inside. So inside, once again, it represents the center of the solenoid. Okay, so calculate the length of the wire forming the solenoid. So now you want to calculate the length of the wire. So remember, this is the shape of the solenoid. Okay, it's a spring-looking thing, a helix shapes. Okay, a spiral shapes. So the questions now ask you to calculate the length. So it means that it wants the length in a straight line. Okay, so you have a solenoid. This is a solenoid shape. This is the length. So the length, the L is equals to how many? Okay, what is the length? Okay, I'm going to change the symbol. I don't want to use a small letter L. Capital letter L for unknown length. Okay, because small letter L, I'm going to use it for the calculations of a B. So I have a diameter right here, D. I have a current I. and then I have B. Okay, I have B. So how am I going to solve these questions? Okay. If again you look at this question, A solenoid. So A solenoid means that now you have one solenoid, all right? One solenoid. So now let's see. Okay, let's see. How am I going to solve it? So again, it is a solenoid question. B equals to mu naught and I. Okay, B equals to mu naught and I. And then do I have the small letter n? Obviously, I don't have. Okay, obviously, I don't have. So I'm going to expand these equations to become mu naught Ni over L. Now, why? That is because I want to know how many turns in this solenoid first. Okay, in order to calculate the length, you need the number of turns. Okay, you need the numbers of turns. So you cannot determine the length without number of turns. So given B equals to 2.3 times 10 to the power of negative 3 equals to, now mu naught is 4 pi times 10 to the power of negative 7. N is an unknown. I given 18. Length given the length of the solenoid. Okay, this is the length of solenoid. The length of solenoid and the length of the wire forming it, they are two different things. So length of solenoid is 1.5 meter. Rearrange the equations, you will obtain a value with decimal point. Okay, you obtain a value with decimal point, which is 152.5 turns. Now, when it comes to number of turns, it shouldn't be a value with decimal point. All right. So what are we going to do? Okay, n is then equals to, you let it approximate to a 152 turns. Okay, you round down the value. Okay, tak round up, kita round ke bawah. Okay, you round it down. So 152.5, according to the mathematics, it should be equals to 153, right? But in physics, no. Okay, we don't take 153, we take 152 because we want to have a complete turn. Okay, a complete cycle. So if you round up to 153, that is not a complete cycle. The last cycle is incomplete. Then you cannot call it as one turn. Okay, therefore you need to round it down. The numbers of turns that we have is 152, the complete number of turns. Okay, complete turns. So now calculate the length of the wire forming it. How to calculate the length of the wire forming it? So one turn, this is one turn. Okay, satu turn. So the circumference of the turns, kita tengok, okay, lilitan. Okay, lilitan. I don't want to give it this one. This is a turn in the solenoid. Okay, the solenoid. So one turn. One turn, let's look at the circumference. Okay, the circumference. So let us look at one turns equals to how many meter. Okay, circumference is equals to 2 pi r, which is then equals to 2 pi 1.3 times 10 to the power of negative 2. It is equals to 8.17 times 10 to the power of negative 2 meter. So one turn equals to 8.17 times 10 to the power of negative 2 meter. Therefore, okay, therefore the length, okay, length equals to number of turn time circumference, which is then equals to 152 times 8.17 times 10 to the power of negative 2. So the total length needed to form the solenoid is equals to, okay, wait, yeah, 152 times 8.17. 1.124. Okay, 12.24, 12.4 meter. Okay, 12.4 meter. This is the length needed. The length needed to make a solenoid. Okay, to make a solenoid given in the questions B. So that is the final answer. All right, that is the final answer. So now I give you, okay, I give you a few minutes to write it down before we proceed to the next question. Okay, so soalan ini dia special sedikit sebab dia tanya panjang wire yang diperlukan untuk buat solenoid. Dia melibatkan current and resistance. Okay, tapi kalau anda tengok step by step, it shouldn't be an issue for you to answer this type of question because they are just a combinations of all fundamental things. Okay, so basically we're done with magnetic field. So as you can see, magnetic field is very simple. Okay, and the three examples given in your books, actually they already cover all sort of questions that could be asked in a magnetic field. Right, dia tak susah kan? Kamu tengok 4 soalan ini macam senang je. Okay, so 4.3, now we are moving on to a magnetic force. Okay, so once again, the way to solve magnetic force, the idea to solve magnetic force is exactly the same. You look at the object. Okay, so when it comes to magnetic force, there are 3 possible cases. The first one is when you have a moving charge particle. Okay, moving charge particles. When it comes to moving charge particles, the equations to be used is F equals to QV cross B. Okay, which is your QV. Okay, your magnitude is equals to QVB sine theta. Now, the things that you need to know is this angle is the angles between. Okay, whenever you forgot about this angle in between, where you refer to the original equation. Original equation, it tells you V cross B, meaning that this is the angle between V and B. All right. And then if you look at the second case where you have a conductor, a straight conductor, right? A straight conductor. So when you have a straight conductor, the equation is F equals to IL cross B, which is F, the magnitude of the force, is equals to ILB sine theta. So once again, this theta is the angle between these two vector product. Okay, so it is the angle between L and B. Now, L, of course, is a length, okay, it's the wire itself. So the third possible case, okay, the third possible case is when you have two straight conductors. So just now it's one straight conductor, and then now you're dealing with a case with two straight conductors. Okay, two straight conductors. So when you have two straight conductors, the equation is just equals to F equals to, okay, the equation is, let me see, mu naught I1 I2 L over 2 pi D, the force between the two of them, between the two conductors. So as long as you know which case you are looking at, once again, you know which equations to be used. All right. And of course, the directions, you need to determine the direction. When it comes to moving charge particle and one straight conductor, you can straight away determine the directions by either using Fleming's left-hand rule, okay, Fleming left-hand rule, or right-hand grip rule. It is totally up to you which one to use. Okay, dalam kelas saya tak paksa Anda mesti ikut cara saya. So right-hand grip rule is the rules that you already learned in chapter 1, Sem 1 for the cross product. Any cross product, you can use it to determine the force, okay, to determine the direction. And one thing that you have to remember when it comes to the moving charge particle, okay, when it comes to moving charge particles, thumbs give you positive charge. Okay, thumb give you positive charge. When it comes to moving charge particle, thumb represent the force, okay, the force acting on positive charge. Okay, the directions of the force, okay, the directions of the force acting on positive charge. If you have a negative charge, then it is simply opposite to the directions of the positive charge. Okay, so negative charge, okay, negative charge, just opposite direction, okay, opposite to the directions of positive charge. So if you got the directions thumb pointing upward, but now you have a negative charge, then it simply means the directions of the force acting on negative charge is pointing downwards. Okay, thumb tunjuk ke atas, direction untuk negative charge menuju ke bawah. Dia terbalik dengan thumb, terbalik dengan arah untuk positive charge. That's it. Okay, so you stick to left hand, okay, Fleming left hand rules, or you use right hand grip rule. But for both rules, the thumb represent the force acting on the positive charge. Okay, the directions of the force. Okay, the directions of the force for negative charge acting on acting on positive charge. Okay, positive charge. So if you're looking at negative charge, then always remember it is just opposite to the directions of positive charge. Okay, dia punya force. So bermaksud kamu punya tapak tangan, okay, tapak tangan di belakang, bawah, okay, opposite to the thumbs. That one is the directions of negative charge, right? Now, when it comes to two straight conductor, it is slightly complicated. Why? Because it involves a two-step, okay, two-step in determining the direction. Step one, you need to determine the directions of magnetic field first. Okay, determines the directions of B first. Okay, I will show you how after this, don't worry. But this is just a summary. And then followed by step two. Okay, so step two, you determine, okay, determines the directions of force. Okay, either by using Fleming left hand or right hand grip rule. Okay, Fleming left hand or right hand grip rule. So the idea is very similar, okay, just that it has an additional step. Okay, it has an additional step. So before I look at the questions, before we go through the questions, I give you a few minutes to write down the summary. Okay, few minutes for you to copy down the summary. You can write it down in your books before we proceed to example 4, 5, 6, 7, and 8. Okay, we'll discuss until example 8 today. So I give you a few minutes to write it down. Right? So this is just some very brief summary, and all of this we have already mentioned in a lecture. Okay, just that now I summarize them into a short mind map for you guys. You can copy in a form in a way that you're comfortable with. Okay, cara yang kamu rasa selesa nak tengok, nak baca. So semua itu Anda boleh tulis dengan tulisan sendiri. Okay, kelas saya tak paksa kamu mesti ikut saya punya cara. Saya bagi Anda beberapa pilihan. Okay, Anda buat ikut cara yang Anda rasa selesa. Okay, now let's look at example 4. Example 4, I won't be discussing with you because it's quite hard to show it to you without a face-to-face slot. Okay, you can go through the video in YouTube. I've already posted all those links in your group. So now I will just give you the direction. Okay, I'll just give you the directions. But make sure you tried it. Okay, make sure you tried it. So this one is into the page. And then this one is going to the left-hand side. and this one, the force is also going to the left. Okay, make sure you try it because you are going to need all these direction in your assignment. Okay, assignment definitely will have questions that involve direction. So you need to know how to determine the direction. You need to practice until you can get the right answer for all 3 questions. So example 5. Okay, so directions, you just copy it down and then you try it during your free time. Make sure to try it. If you are having issue, you go through the video. Okay, you go through the video. So example 5, calculate the magnitude of the force on a proton. Okay, so now you are given an object proton. This is a positive moving charged particle. Okay, positive moving charged particle that's traveling with a speed 5 times 10 to the power 7 meters per second in the uniform magnetic flux density. Uniform magnetic flux density, that is your B. Okay, that is your B. So if the velocity and the velocity of the proton is perpendicular to the magnetic field, so now it tells you V and B, they are perpendicular to each other. So how do we know, how do we determine the direction? Well, recall the things that we mentioned just now. Theta is the angle between V and B. So now question tells you V and B, they are perpendicular to each other. Meaning that theta in questions A is equals to 90 degree. Okay, it's equals to 90 degree. So now you have a moving charge particles. The equations B is equals to QVB sine theta. Okay, you are given the no, I'm giving you the wrong thing. F equals to QVB sine theta. Then according to the informations given, now you have the theta, and then you have B, you have V. How about Q? So remember, proton is an elementary charge. Okay, elementary charge. So elementary charge, the value E is given in the list of constant. Okay, list of constant, which is equals to 1.6 times 10 to the power of negative 19. So it is a constant value. Whenever you have proton or electron, the values, the charge is given in the list of constant under the terms elementary charge. So kamu jangan pergi cari list of constant, kamu cari mana proton, mana electron. No. Okay, you won't find those 2 terms in your list of constant. It will just mention elementary charge. Okay, kamu punya elementary charge E. So E is equals to 1.6 times 10 to the power of negative 19 given. So now what are you going to do? You just plug it into the equation. Okay, you plug it into the equation, you put everything into the equation. Make sure now your calculator is in degree mode. Okay, because this is 90 degree, so degree mode. So if you got everything right, the force should be equal to 1.2 times 10 to the power of negative 11 Newton. Okay, 1.2 times 10 to the power of negative 11 Newton. So for questions B, basically you just repeat the same thing. Now you have angle 50 degree, okay, between velocity and magnetic field. So given theta is now equals to 50 degrees C, so F once again is equals to QVB sine theta. Plug in the value. Eventually, you should obtain 9.19 times 10 to the power of negative 12 Newton. The last one, the last question C. Velocity parallel with the magnetic field. Now, parallel means that the angles between them is 0 degree. Okay, if you have 2 parallel vector, means that the angle is equals to 0 degree. So F equals to QVB sine theta. This one you don't even have to calculate. Straight away, it is equals to 0 Newton. Why? That is because sine theta, if you have a sine 0 degree, it gives you 0. Okay, it gives you 0. And when you look at questions A, B, C, okay, when you look at these 3 questions, questions A, questions B, question C, according to the values and the angles given, okay, it shows you that as the angles increase, the value, the force increase. And it also proves that you have a maximum value, okay, F is maximum when theta is equals to 90 degree. and then F is minimum when theta is equals to 0 degree. That is because of the sine theta. Okay, that is because of the sine function. If you have cos function, cos 0 is maximum value, cos 90 degree give you minimum value. But now you're looking at the sine function. Okay, now you're looking at sine function. Therefore, force is maximum if the angles between velocity and the field is 90 degree. It is minimum if they are parallel to each other, right? So, okay, I will give you 5 minutes to write it down, including this one. This is very, very important. This type of questions usually will comes out in your objective question. Okay, bagi Anda 5 menit, catat semua dan pastikan Anda buat substitution yang lengkap. Alright, masa saya tunjuk Anda shortcut, Anda buat substitution yang lengkap. Buku Anda buatkan dia kemas dan lengkap. So I give you 5 minutes to complete everything. Okay, try to calculate it, see whether you can get the answer or not. Okay, so now let's look at the next example, example 6. Example 6, an electron at point A in figure above has a speed. So once again, you're given speed, V equals to 2.5 times 10 to the power of 6 ms negative 1. Now given E, this E is the elementary charge. So electron, once again, is a form of elementary charge. It is a moving charge particles, okay? A negative moving charge particle. All right. So the magnitude and the directions of magnetic field that will cause the electron to follow the semicircular path from A to B. Now, if you look at this diagram, okay, how to determine the direction? First thing, you need to know the directions of F. Otherwise, how are you going to determine the directions of magnetic field, right? So in order to determine the directions of magnetic field, you need the directions of the force. What is the directions of the force? Now, this is a semicircular path, a circle. Remember the things that you have learned in chapter 1, Sem 1, chapter 6. If your object is moving in a circle, it means that there is a centripetal force that is heading towards the center. And the centripetal force is just the name of the net force, okay? Centripetal force cuma nama untuk net force. The force that causes the object to move in a circular motion. So in this case, the force that causes my object to move in circular motion is FB. Okay, so FB is acting as a centripetal force in my situation. Therefore, FB is pointing towards the center. So from here, you can then determine the directions of magnetic field. Okay, dari sini kamu boleh tentukan arah magnetic field, where the direction is into the page. Okay, into the page. So remember, now you have a negative charge particle. So your thumb, okay, the direction that is opposite to your thumb is the direction of the force. Okay, so force going to the right-hand side. When you want to determine the directions by using your Fleming's hands rule or your right-hand grip rule, you let your thumb pointing to the left. Okay, your thumb to the left. Sebab apa? Sebab sekarang kamu ada negative charge. Okay, thumb to the left because now your force given right here, force for negative charge is going to the right. So you let your thumb going to the left and then velocity going up and you will be able to determine the directions of magnetic field, which is into the page. Okay, which is into the page. So this is the crucial part. Okay, crucial part for you to determine the direction. Okay, now how about the magnitude? You have a moving charge particle, so you don't have to think about the equations that you have to use, right? So you have equations. F equals to QVB sine theta. But then, if you look at the questions, you don't have enough information, right? You don't have a, okay, you have a Q, okay, you have a force only, okay, you have the force only, but then can you determine the B? Cannot, okay, you don't have force. You don't have force, you don't have B. Okay, you do have theta, which is 90 degree. Okay, this theta is equals to 90 degree. You do have Q. Okay, you do have V, but you don't have magnetic field. That is the things that you want to calculate. You don't have magnetic force. Then we need another alternative method to solve it. So let us recall. Now my object is moving in a circular path. Aha, circular path. I think I can do something with it. So let's say now I have FC equals to MAC. And the force causes my object to move in the circular motion is FB. So FB equals to mv squared over r. FB at the same times I have this one. This is my FB. So QVB sine theta equals to mv squared over r. So from here, I can then simplify it. Okay, simplify it. And then I plug in the value. Do I have M? Yes, I do have M. Okay, so do I have R? Yes, I do have. Because questions give me the diameter is 20 cm. So radius is 10 cm. Yes, I do have R. Angle, yes, I have it because my V is going up. My B is into the page. So they are 90 degree. Okay, they are 90 degree between V and B. And then I have Q because it's the elementary charge. Plug in the value and rearrange, you should obtain B equals to 1.42 times 10 to the power of -4 Tesla. And it is into the page. Okay, it is into the page. So that is how you solve it. Okay, that is how you solve it. So this object is moving in a circular motion. Therefore, FB is equals to FC. Okay, FB is equals to FC. The force that causes my object to move in circular motion, to move in a circular path. So questions B, the time required for the electron to move from A to B. So you record the things that you write in your lecture. Okay, you write down in your lecture notes. So we have V equals to, okay, V equals to R omega. Okay, V equals to R omega. One circle is 2 pi over capital letter T. So from here, we arrange the equation. Period is equals to 2 pi R over V. Plug in the value, you will obtain period is equal to 2.51 times 10 to the power of -7 seconds. But since the semicircular path, okay, from A to B, okay, from A to B, it is a semicircular path. Therefore, the time taken is equal to half of the period, which is equals to 1.26 times 10 to the power of -7 seconds. So that is how you solve this question. Okay, that is how you solve this question. So moving charge particle, if you have a charge moving in a straight line, straight away you can apply QVB sine theta. But if it is moving in a circular path or semicircular path, usually we have to use this relationship when it comes to circle or semicircle. Okay, semicircular path. Usually we have to apply this concept. All right. So the important thing in this question, let me repeat it again. First, how you determine the direction for the negative charge, you let your thumb pointing to the left. Okay, because now the diagram given, force is going to the right. So when it comes to negative charge, your thumb should be pointing to the left, opposite to the directions given. Because directions given, that is the thumbs, originally the thumb is for the positive charge, right? And then the second important thing, if your object is moving in a circle or a semicircular path, usually we need to use a relationship FC equals to FB. Okay, that is the concept. That is a concept. So if you got write this down, usually you will get 1 mark for the concept. Okay, and then how to calculate the time taken for semicircular path? Time taken for semicircular path is half of the period. So you obtain the period first, and then you calculate half of the period. So that is the important things in example 6. Okay, so once again, I give you a few minutes to write it down before I proceed to example 7. Write down the important things in this question, especially how to determine the direction. Right, now let us move on to the next question. So example 7, again, when it comes to the directions, I will just give you the answer. All right, and then you try the questions and then you check your answer through the YouTube video given. Okay, so the force is going to the left for the first question. Second question is going to the right. Okay, and there's a corrections in your learning outcome right here. Okay, we use small letter L. F equals to IL cross B. Okay, we use small letter L to represent L. Okay, now let's look at example 7, example 8. Okay, example 8. Oh, we have one more example 9. Okay, example 8 and example 9, the last two examples for today's slot. So after we are done discussing, then I will let you guys go. So a wire of 20 cm long, okay, this is your wire, is placed perpendicular to the magnetic field. So this is your B. Okay, so magnetic field given 0.4 Weber per meter square, length is 20 cm. Now, perpendicular, you look at the equations once again. Equations given, F, okay, F is equals to IL cross B. So if you calculate the magnitude, F is equals to ILB sine theta. Remember, this theta, it always represents the angle between L and B. So L and B, they are now perpendicular to each other, meaning that in these questions, the angles given is equals to 90 degrees. Okay, angles given is equals to 90 degrees. So how are we going to solve it? Okay, how are we going to solve it? Calculate the magnitude of the force on the wire when the current I, 12 ampere, is flowing through it. So now I have L, I have B, I have I have theta. Straight away I can get the answer, you see. So F equals to ILB sine theta. Plug in the value and you should obtain 0.96 Newton. Okay, 0.96 Newton. Very simple. Okay, so this is a one straight conductor questions. So you just apply the equation for a straight conductor. Okay, because wire represents straight conductor. Okay, wire, in our case, it is a case of a straight conductor. Okay, a straight conductor. Questions B. For the same current in A, now your I is still 12 ampere. Okay, that is the information that we have. Determine the magnitude of the force on the wire when its length is now extended to 30 cm. So now L is no longer 20 cm, L is 30 cm. But B is still the same, okay, because the question didn't say anything about the magnetic field, and the angle is still 90 degree. Okay, 90 degree, because the question didn't mention about any changes on the angles, didn't mention any changes on the field. So you can assume they remain constant. The only things that is changed is the length, okay? That has changed is length. So now you just use F equals to ILB sine theta. You plug in the new information and you should obtain 1.4 Newton, okay? 1.4 Newton. So that is for questions B. Now question C. If the force, now the questions give you the force, okay? Instead of the length, instead of the currents and so on, now it gives you force. So force is equal to 60 times 10 to the power of -2 Newton. And then wire, now the length has gone back to 20 cm. Okay, and the current I is equal to 12 ampere. It didn't mention anything about angle, right? So let's assume it is 90 degree again. If it isn't being mentioned in the sub-question, then we use the information from the main question. Okay, kalau maklumat tidak diberi di dalam sub-question, then kita rujuk kepada main question untuk dapat maklumat tersebut. So main questions beritahu kita angle 90 degree, therefore we can keep it as a 90 degree. Okay, if it is mentioned that now the angle decreased to maybe 70 degree, then you have to use the new angle in sub-question. So priority kita pergi kepada sub question. Kalau sub question tak ada punya maklumat, baru kita tengok main question. Kalau main questions pun tak ada, then baru kita rujuk kepada list of constant. Itu dia punya urutan. Okay, itu dia punya urutan yang kita mesti ikut. Priority diberi kepada siapa? Priority is given to the sub question. If no, okay, if you couldn't find the information from the sub question, then you refer to the main question. Okay, if it still cannot be found in the main question, then it could be a constant value. Then you try to look for it from the list of constant. All right. So now that you have all this, you want to find B. So F equals to ILB sine theta. F is 60 times 10 to the power negative 2 equals to I given 12. L is 20 times 10 to the power negative 2. B is an unknown, and then sine 90 degrees. Rearrange the equation. B is equals to 0.25 Tesla. Okay, 0.25 Tesla. So that is how you solve example 8. All right, so 3 questions, 3 simple questions. I give you 3 minutes to write it down. Then we will proceed to example 9, the last example for today's class. So 3 minutes for you to write it down. Okay, so now let us move on to the last questions. Okay, now this question. Too long, okay, now you see the first statement already tell you which equations to be used. Two long straight parallel wires. You have a case with 2 straight conductors. In a vacuum, they are 0.2 meter apart. So this is the D distance between 2 wires. The wires each carry a current I in the same direction. Each carry a current, meaning that I1 equals to I2. Okay, I1 equals to I2. And the keywords again is in the same direction. Questions 1. Draw a sketch showing clearly the direction of the force on each wire. So this is the questions where you have to apply the two-step recipe that I gave you just now. So now let's see. This is a straight conductor. Let's sketch a straight conductor first. This is a conductor 1. This is a conductor 2. Okay, this is a conductor 2. So now it tells you current, they are flowing in the same direction. Let's assume both of them, they're heading upwards. Okay, your I1 and your I2. Okay, now when it comes to this type of questions, okay, step one, you need to determine B first. Determines the directions, okay, the directions of B hitting. Kita nak tengok yang hitting, not generated. Okay, not generated by wire 1 or wire 2, but that is hitting wire 1 and wire 2. Okay, we want to determine the directions of the B that is hitting our wire 1 and also wire 2. Now, if you look at this diagram, wire 1, when it has current flow, of course, it will generate its own magnetic field. When it generates its own magnetic field, the magnetic field generated by it, it won't hit itself. Okay, what is going to happen is that the magnetic field generated by this wire 1, it will hit conductor 2. Okay, it will hit conductor 2. So what are you going to do? You use your right hand grip rule, you let the current flowing upwards, and you see what is the directions of your forefinger when it hits conductor number 2. Okay, when it hits conductor number 2. So you use the directions of I1, and then you determine the directions of B1 when it hits your second conductor. So if you do it rightly, okay, if you do it correctly, then you will see that B is into the page. Okay, B is into the page. Kalau kamu buat dengan betul, okay, if you use your right hand rightly, okay, correctly. So now if you repeat it again, okay, this is your B1, okay, B1. If you repeat it again, now you let your finger pointing upwards as shown in I2, okay, just now you use I1, now you use I2, okay, now you use I2 to determine the direction. The directions of B2 that is hitting wire 1. Okay, B2 hits wire 1, B1 hits wire 2. Alright, B1 generate by wire 1, tetapi dia hit wire 2. B2 generate by wire 2, tetapi it hits wire 1. Okay, make sure you don't get confused between the term generate and hit. So if you do it in a right way, okay, in a correct way, then you should obtain a B that is out of the page right now. This is your B2. B2 is out of the page. Okay, out of the page. So B1 into the page, B2 out of the page. So from there, you then determine the directions of the force. So your I, which is your L, is going up. B2 is out of the page. Then the force would be going to the right-hand side. Okay, so this is your F21. And then if you do it again for wire 2, with the B into the page and L going up, the I going up, then you should obtain the force going to the left-hand side. This is your F12. From 1 on 2, from 2 on 1. Okay, 1 on 2, 2 on 1. 2, 1 bermaksud 2 on 1. 1, 2 bermaksud 1 on 2. Okay, so that is how you sketch the diagram. Okay, that is how you sketch the diagram. So the distance between them, you also need to show it in your diagram. Distance between them is D. Okay, it's a D. So kamu buat dengan elok lah. Okay, ini saya just a sketch for you. Okay, you do it nicely in your own book. So calculate the force between the wires per meter. Okay, it's asking for force between the wire per meter. Force per meter, F over L. So F over L equals to mu naught I1 I2 over 2 pi D. So plug in the value. Okay, you have I1 equals to I2, which is both of them equals to 2.4. And then distance between two wires is 0.25. Then you should obtain 4.6 times 10 to the power of -6 Newton per meter. Okay. 4.6 times 10 to the power of negative 6 Newton per meter. So that is how you solve question number 2, right? That is how you solve question number 2. Now let's look at question number 3. Question number 3, the current in one wire is reduced. Reduced to zeros. Reduced to 0.64. Calculate the current needed in the second wire to maintain the same force per meter of their length as in questions number 2. Okay, ada sedikit typo di sini. As in questions 2. So you want to maintain the same F over L, meaning that for this question, F over L is equal to 4.6 times 10 to the power of negative 6 and M negative 1. Now you have I1 equals to 0.64 ampere, I2 equals to unknown. That is the things that you want to find. You want to see what is the current needed in order to maintain, okay, to maintain this value. And then how about all the other variables? Like I told you before, if it is not being mentioned in the sub question, then you refers to the main question. Main question tells you the D is still equals to 0.25 meter. All right. So now that we have all of the information needed, let's apply F over L equals to mu naught I1 I2 over 2 pi D. F over L 4.6 times 10 to the power of negative 6 equals to 4 pi times 10 to the power of negative 7. I1 0.64, I2 is an unknown, divided by 2 pi D 0.25. Rearrange the equations. I2 is then equals to 8.98 ampere. All right, 8.98 ampere. So you need to increase it quite a lot in order to maintain the same force between these two wires, right? So I think that's it. Okay, so I want you to write it down. Okay, I want you to write it down first.